Good? Yep. Okay. All right. Hi. I'm not going to lie. The past 2 days have been very difficult. I've learned a couple of things. First thing I learned was that I shouldn't do this thing when I'm kind of tired, which I was in the past couple of days, and it's been hard. It's been tough. Second thing I learned was that software development is actually pretty hard, like it's super hard. So yeah, that's the one thing. That's the second thing rather. And then finally, I can't remember the other thing. But anyway, today what we're going to do is we're just going to finish up, well not finish because this stuff is never done, but we're going to like tie up any sort of loose ends that we've got in our MPEG transport stream package, do a bit more testing and stuff, and just a quick bit of documentation wherever's left. And then I'm pretty happy with where it's at. Like I know that like the functionality that it provides is, that's like minimal and viable. So it's like useful. It doesn't do everything that MPEG transport stream, like it doesn't handle all of the data that you could possibly transport with MPEG transport stream in the headers, in the metadata at least. But that's okay, So yeah, let's just get going because, yeah, let's stick to the action, I guess. Yeah. Oh, sorry, shit. One more thing is that now after MPEG transport stream, after this little session, I think now, I'm thinking of what to do next. And I think what I'm going to do is RTP, or the real-time transport protocol, or real-time protocol. I always forget which way around it is. This is used in things like WebRTC. So if you use like, Google Meet or any of these sort of Zoom video call things, it's used in like FaceTime. It's used in, what else is it used for? Yeah, just any time where you need to, send some video, audio, and you want it to get there, in a sort of real-time interactive way, then RTP is handy for that. It's just done over UDP, and yeah, it doesn't do much. It's used in conjunction with a whole other suite of protocols, but I think we're just going to see more and more of this kind of thing. And yeah, I think it should be fun. Okay, action. So here we are. And yeah, I promise that this time I'm going to be a little bit more on the ball, I think, because yeah, I'll tell you what, it was difficult next. Yeah, the last couple of days. So for anybody who, for some crazy reason, watched a long way through the sort of second half of yesterday and the days before activities, I've fixed up pretty much most of the crazy bugs that sort of introduced or found. So let me just update this thing and then let's see what we got going. Oh yeah, okay, good. Just close that. What I might do is just so these are the two serious patches that we needed to make, but this is probably the most important one here. So really, whatever this was not right. Okay. So this is the big endian. So what we wanted was 33 bits, 8, 16, 24, 32, 40, no, 33. So this is getting the leftmost bit out of this byte to get us 33. Now we've got these zeros here because what we're actually doing is we're kind of faking it by saying, hey, we have a big endian uint64, just so that we can use this sort of function in the standard library. Also because we can't, that's like the way, I guess, to represent a 33-bit integer in Go and still be able to do like integer-like things with it, like add things, subtract it, you know, like assign it to variables super easily, that sort of thing. Iterate. Yeah, so with storing that as a uint64 and then we're on. The other pretty tricky bug was this one here. So basically in a MPEG transport stream packet, we were trying to decode the contents of the packet. We weren't being clever enough there. So there was another little bit of logic that we needed to detect whether there may be a what's called a PES packet in the transport stream packet payload. So if I just, exactly what I mean by that, should be clear if I just look at the docs. So we go here, and then we look at our, here, packet, okay. So we've got our packet and some fields, and then in the payload, and one of the things that we can actually decode from the payload is this thing, a PES packet, or packetized elementary stream. So this is the thing that'll often contain, or that will contain the actual raw video and audio data in there somewhere. The thing is that we were reaching into this payload a bit too, as I said, yeah, we weren't doing it very, we were just kind of doing it based on a very silly thing, not enough information. And so we ran into weird bugs where there was actually, we were guessing that there was this in the payload by reading the first 3 bytes of this. Now, of course, eventually we were reading a stream and we said, oh, hey, there's those 3 bytes. Now, it was just coincidental because there was actually no PES packet in that payload. But we were trying to decode one and getting all sorts of crazy values that didn't make any sense. So fix that one up. And yeah, look, that's pretty much it. So it was not very exciting. That's 2 days worth of work explained in about, I don't know, what's that, like a few minutes? So there we go. And it's like barely any code, right? Like, you know, what are we talking here? Like 3, 4, 5, 6 lines? I don't know. Yeah. But that's how it is, I guess. I read somebody the other day was saying, hey, Travis, how you going? I read somebody the other day, somebody saying, low level programming. Oh yeah, is that the type of programming where you're reading like 99% of the time and writing code 1% of the time? I thought, yeah, actually, I never thought about it like that. But if I think back over the past few weeks, it's absolutely been like that, right? Just been reading these specs over and over again, and maybe, you know, typing like, oh no, we got 3, or is it 4, and then just sitting there, just looking at it and trying again and again. So yeah. Anyway, it's fun though. So we've another program. Yeah. Nice. That's cool, cool, cool. Also in Go, I guess? Okay. What I want to do here is right now our only sort of test is, well, it's not our only test, but this is about 4 seconds worth of video from Big Buck Bunny. What we can do here is actually just we're going to read in all of Big Buck Bunny and just dump it in here. Just a test for now, but later on I think we're going to, just like with the other packages that we've worked on, we're going to like sort of finish MPEG transport stream, but not really. We're just going to like move on to developing some other thing, and of course we're going to come back to it just like we've done for SCUDdy, M3U8 for HLS and the other ones. All right, anyway, so let's get this thing in. So we'll go streams. Oops. Let's grab that. And then we're going to set this to real time because we're sort of, oh, actually, no, sorry. No, we're not. I ignore what I was saying. And then we're just going to write that, copy the codec, write in one MPEG transport stream file to bigbuckbunny.ts. Work it all out automatically. I think that should be all right. Cool. Okay, let's leave that to download for a sec. I'm back on my my Mac here just because my neck was like and shoulder were really messed up yesterday, so got a nice taller screen here rather than looking down at the laptop. That was bad. I found that out because when I was actually watching back some of the video just to check if the audio and the lights and sound and, well, especially the audio, but and the latency as well was okay. And I just saw me looking down like this at the screen and I thought, oh man, my poor neck. Oh, yep, okay, we got it. So what we'll do is we will let's instead read from Big Buck Bunny. Sweet, okay. So what this test does is that it reads through every single byte of the file, decodes a byte, encodes it again, writes it back out, and then it checks if the byte that it got in is the same as the byte that went out. And according to us, it is all exactly the same. So that's awesome. What we could do probably is, we've got this little command here, this transport stream pipe or TS pipe. What we could probably do is just amend this program to actually read in the whole of Big Buck Bunny. Let's try and watch it at like 2x speed, or try and seek around and see if like anything's really busted up. Yeah, so let's do that. So we've got a scanner now that we can use. New scanner, and we're going to read that from standard input. Now we can go like this for scan. Let's and so we're just going to decode the packet, which is done by the scanner. So we're going to go packet is the current packet in the scanner. What we can actually do is just go, I can actually just do it in one go. So write encode to standard output from the scanner's packet. to if we get an error, we're going to print out the packet that we're up to, and then the error. And then also just, I think that's it. Yeah, that's the whole thing. Okay, and then we'll just check for a scanner error. Cool. Right, so let's run this program on reading that. We're going to read from Big Buck Bunny, and we're going to write it to, just put it there. Oop. Oh, there's no error. We're not storing it as a value variable. If not equal nil. Cool. Okay, there we go. So ran okay. Let's oh yeah, I've just updated the operating system on this, so we've got a few. Okay, cool. I assume. Can we hear that? Ah, hey there. Hello, fellow byte decoder. Yes. Oh yeah, I can hear it. So this is our re-encoded thing. Let's try and stick around and just, I don't know. Looks good though. We're byte for byte identical, so I mean, it should be okay, right? Now, before we were actually byte for byte identical, but we were not. We were, most packets were not. So what was actually happening was we were reading through the file, and at like we're reading through Big Buck Bunny at about packet 30-something thousand, packet 33,000. Then one of the values that actually was there's a clock in the transport stream packet. What was one of the clocks? The value was getting pretty high, and then yeah, our program didn't quite handle that. So yeah. Shouldn't I read RTC instead of or RTP? Yeah. Okay, that looks good. One of the things that's good to do as well is VLC has a handy shows you like a handy little log of when it's playing back stuff. So let's watch that as it goes, just to see. I mean, I just don't know. Now, often VLC will tell you about all sorts of things, like even on what you'd think are 100% valid files. But yeah, that's part of the fun, right? And where am I going? To streaming. Yeah. There. Okay. Messages. Shit. Okay, well, that's the best I've ever had it. Wow, that's great. Are we getting audio? Shit, sorry if that's really loud. Yeah, that's okay. That's just me pausing and stuff. Ooh, yeah. Deadlock. Yeah. Cool. Okay. Well, that's great. Oh, holy shit. Okay. So that's, yeah, nice little interface. Ooh. Good stuff. Okay. Now I've actually done more documentation than I realized. Maybe let's have a look at the rendered stuff. And yep. So what I could probably do now is actually just have an example. I think I'd like to put it at the very top, so have like a whole package example, something like that. And we'll have a thing that is, you know, maybe like just a little program that reads from the reads from standard input, writes to standard output or something, but then just prints out the maybe like the clock reference of any packets that have one to standard error. So it's just like a handy little debugging thing. And this is what is actually done by ffprobe. So if you go into here, or at least let's do here. So if show packets, we run that. This is, you know, about the same functionality, but of course ffprobe is all written in C, and yeah, it's a very big program, whereas ours is not. Although it does, you know, require the whole Go runtime, but hey, you know. Cool. Yeah, so let's there was a patch that Black Falcon sent in, but where was that? Scotty 35 MPEG-TS. Oh yeah, here we go. Yeah. Okay, yeah, we want to do something like this. So what we could probably do is just have a new file, MPEG-TS test. example. Oh no, the buffer, I'm so used to writing that. So this is going to be MPEG-TS new scanner from standard input. Let's just print out, you know, look at the doc. So if there's a PCR, that's in the adaptation field, I think, if I remember rightly. Yeah, okay. So what we want to do is let's do something like this. And then a tab, and then let's just print out the clock reference in there. We'll go if equals the packet, and then if packet dot adaptation equal nil, and gonna work? Yep. And we do packet dot adaptation dot PCR. Oh, let's do a little, spell it out a bit more in the example. And I'm not sure how to document that example yet, but I think, oh, sorry. And then also we'll write it back out again. So packet, blah, 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 blah. Okay, and then we write it back out again. So we're going to go ts.encode to standard output, our packet. So this, just quickly do a bit of doc, something like, sure the standard way to word this is, just quickly have a look at maybe the P package, get. Oh, okay, so maybe need a package with a, oh, some good package documentation there. Maybe strings. R package. Here we go. So it looks like what they do is yeah, example under, yeah, that's it. Yeah, okay, let me do that first. Let's rename that file. Okay. I think that reads okay. Let's just format that. Standard error. To the wait, why didn't that render correctly? I guess that'll get rid of mine. Yeah. Does it need to be like that? And then it reformats that as well. How weird. Yeah, probably something to do with GoDoc. That's fine, whatever. Okay, awesome. That's great. I'm really happy with that. Let's just yeah. And then just add example, add a package example. Document package, add package. Package. Why is this so hard? Add. Cool. Oh, did I just FF probe? Yeah, okay. All right. Cool. Cool. Really good. Okay, well, maybe what I might do now is go out and grab some lunch, and then, yeah, come back and just maybe we can look at RTP. I mean, are we really gonna do that already? Why transport stream and not MKV? I guess I found transport stream interesting because it has like really weird, like it has been used in the real world in ways that, yeah, like it's strange how it's used both in like HLS, and for like, you know, terrestrial radio and TV, and also even to like deliver internet, you know, like domestic internet. And yeah, and I guess I also found it interesting because yeah, I guess that's it really. Yeah. I've never looked too deeply into the that Matroska container. Yeah, I mean it's you know, it's not really a binary choice, right? I mean, I guess I just happen to yeah, look at transport stream and then yeah. Oh, WebM is based on MKV. There you go. That's cool. Cool. Size comparison between containers. Oh yeah. Oh, so like the overhead versus the actual like the actual content. Cool. Hmm. 4.5% over the. Yeah, wow. That's cool. Is it? I wonder whether it's possible to like do that same kind of weird thing with MKV where you like can just read it from a pipe or like send it over the network. Because that's probably one of the yeah, like the, I guess the weird things, I guess in a sense, about MPEG transport stream is that you've got all of that like in the actual. Oh, I don't know if you can stream MKV. Oh, right. Okay, yeah. So it's really okay, yeah. But I mean, it's weird then. It's like I wonder, did you broadcasting over unreliable and it says multiple video? What a strange. But then, why? I don't know. I mean, like they're so. What? Over unreliable typically contains. Yeah, I mean, because MPEG transport stream has a huge amount of overhead because it contains all of this stuff to synchronize things over unreliable sort of mediums and stuff like that. That's weird that they're almost like two different things. Yeah. Anyway, okay. I'm gonna go get he should have taken PS. Oh, MPEG program stream. Yeah. Yeah, that's true. Oh, anyway, but it's actually interesting, right? Like all of these things are all just a bunch of trade-offs. I think that's what makes this sort of thing interesting, is because like it's yeah, there's kind of like these really like you know, these real world problems, and then you sort of see all of these different kinds of technology to address each different kinds of problems. And yeah, I don't know, it's interesting, yeah. And there's definitely no like yeah, I don't know. Okay, I'm gonna go grab food because I'm absolutely starving. So I'm gonna put on this and then I'll just get the time. It's not even gonna fit anyway. Merci. Okay, I'll do 6:30. Cool. Okay. Thanks. Oh, it won't be that late. It'll be no. Wait. What's the time? 06. Yeah. No. Oh, that's way too late. I'll just do that. Okay. Good stuff. Okay. See you in a bit. All right. Surprise! Here a bit early because, I just love it. Fucking love it. Hey! How are you going? Oh, yeah? What's the, I can't remember which continent you're in. Oh, rough. Well, I'm sure this will send you to sleep because I just want to do a quick bit of refactoring in the MPEG transport stream stuff here. And then after that, well, we're jumping into something jumping into something new. So that might be a bit, you know, I'm going to be looking blankly at the screen for a while, I think. Let's do that. Okay. This is your lullaby, okay? Okay. First up, we can do this nice little... wait, sorry, let me just check that I'm all good here. Yeah, audio's good. Yeah, seems okay. All right. So we're just going to do these nice little trick that... I can't remember his name. Irving? I can't remember. We're just going to do this. And then the same for all of these. And to be honest, I feel like... Anyway, let's do this first, and then I feel like I want to change it to, instead of using the, like that hex value, maybe do the left shift because it's clearer maybe what's going on. So we're going to grab... So that's the first one. And then we'll do that. Because this is, it looks weird, but it's pretty boring code. Because all it's doing is just checking which bits are set in the byte. I feel like... Oh, nah. Let's just leave it like that, and then we can always come back to it. That's already better. Okay, good. Oh. Yep. And again, more of this. Okay, so we can go and we can shorten that up a bit. Oh, yeah. Okay. X20. Oh. Oops. All right. That's probably the last, probably the last place. Do a little bit here, but yeah, I mean, yeah, we're not assigning the value there, though. That's the other thing. So I think that's all right. Let's flags. Yeah. Okay, pretty easy. Hey, easy. Beautiful. Less code, sort of. That's one of those things that it's not really any simpler. It's just less code, which makes it a little bit easier to read, but it doesn't make it simpler. Same complexity. Okay, let's man, are we really going to move on to the next protocol now? I don't know. It's scary. Maybe one of the things I want to do is try and... We're just going to just dive right in as usual. Okay, let's go. Okay, RTP, Real-Time Transport Protocol. Package. RTP implements the real-time transport in RFC 3550. I think, yeah, is that right? Well, I'll do that. Oh, protocol. Now, it doesn't really implement the protocol, but let's just put it there for now, and then, you know, because it doesn't really, yeah, because like the package itself doesn't implement the protocol, right? Like it's going to be something like clients, servers, decoding, encoding, you know, like modification of things like that. So, but we'll get there in the end. I think that this is going to be quite a small one in the sense that like, for now, I only want to do RTP data transfer. But yeah, I mean, let's just grab this thing. So RTP, where do we see it? We see it in Skype, Zoom, FaceTime, Google Meetings. We see it used in like, you know, live production environments. You know, sending video and audio over IP instead of, you know, having like some radio or like running a whole bunch of cable or something. They'll use IP, which is cool. This is, originally it was for like voice calling, and that's also where it's used as well, right? Is in like VoIP services, you know, so if you see any office and they've got like desk phones still, then they'll be using RTP. So RTP itself, like, is like what it says. It's a transport protocol. So you can put a bunch of things in RTP. There's a nice... so these are some of the things that you can transport in RTP. I'm particularly interested in the Opus one because that's a really cool codec, I think. So that's just for audio. So that's like what you use when you're doing like a voice call with somebody. And yeah, of course, we've got stuff for regular old H.264 video. Another one that I think might be fun to do is this very new one, JPEG-XS. So if we're feeling really clever, we might get around to that at some point, but I don't know. I think I need a few, I might need a few donations, but if I'm feeling that brave, it might take a little while or something. Yeah. So yeah, that's, yeah. So these are the things that can be, transported with it. There's all these sort of G722, like these old school, like, I say old school, like, these are the things that, for example, when you do a voice call, like, in like, I think 5G and I think also 4G calling, they actually use RTP. So in the old days, it wasn't like that, right? Like it would go over sort of like a digital, can't remember exactly how it worked. But yeah, now it's, if you do like voice over LTE or like 4G calling, then yeah, I'm pretty sure it uses like a packet-based transport. And I think it uses RTP. So that's pretty cool. It's added right. Okay, so yeah, let's like look. I mean, let's just see what happens. This is a protocol I've never worked with before. So all the work that we've done has sort of has led us to this point. So fuck. I mean, yeah. Let's just see how badly I can fuck this thing up. I believe FFmpeg has a, let's open VLC because I know this does. So in VLC, what you can do is, let's say, for example, you open a file like, oh, yeah. Okay, here's Big Buck Bunny. What you can do when you play back stuff is you can stream the output, and one of the ways you can do that, we've been doing MPEG transport stream, of course, but what you can do is you can do RTP and, oh, I can't remember how that works now. How do you do that? It streams at RTP to that address. So I guess this is going to be using H.264. Let me, hold on, wait, what? I was looking at something else before. Raw, no, that isn't quite what I want to do. Oh yeah, okay, so these are all the options that you can have. All right. Well, anyway, I think what I'm going to do is RTP. I'm going to listen on port 6969. Unicast, yeah. Okay, so we're going to listen to all addresses. Yeah. Sorry, I should have prepared this, but as I said, this is okay. We can open up FFmpeg. Let's go in here. Yeah. Okay. We're going to try and stream this transport stream file from this process, UDP to VLC, just to see, like, I don't know, how it works. And there's a weird flag that is actually, this is actually undocumented in FFmpeg, so yeah, let's see how it works. The other thing we need to set is we need to set it to real-time encode because we're kind of simulating a live stream. It's MPEG-TS. I can't remember what it was now. RTP, MPEG-TS. Okay. Let me get what that is. Protocols. It's actually undocumented. Hold up, let me just find this. Oh, it is that. I was searching it. Isn't documented. Yeah, that's it. RTP is a format or a protocol? Oh, okay, let's give that a go. Okay, whoop, we're sending it. Okay, let's let me just make sure we're doing, it's probably going to be some IPv4 thing, IPv6 or whatever. Quite understand this, but oh, that's the multicast address. Yeah, okay. All right, let me that open. Let's do to okay, sending apparently. How did I do this again? I had this before. Do it again. Oh, it's RTP here. Yeah, okay, let's try again. No? Ah, fuck me. Whoops. Yeah, so all of that's not relevant for us, so it's just hey Assad. Okay, well, another thing we could do is actually just do it from... hey. We could do ffplay, RTP, R6, bzz. Oh, VLC is doing it. Okay, so that's actually... Play for me, baby. Fucking thing. Here. Oh. Oh. Oh, there we go. Okay. All right. There we go. Cool. I don't know if I can... You hear anything? Oh, yeah. Cool. The phrase in freedom movie, that's right, yeah. The free as in free myself from watching this video for the 10,000th time movie. Nice. All right, so we have got that going. Now that's cool and all, but of course what we want to do is actually be able to, like, you know, handle that ourselves somehow. Maybe what we want to do is like receive an RTP stream, extract the, you know, the data out of it, and then maybe just like write it to a file or transport it in some other way, like for example over RTMP to somewhere. All that stuff is possible. So we're kind of, you know, this is really what FFmpeg does under the hood, right? It implements a whole bunch of stuff and then it just gives you a way to pipe the things together. We're doing that in kind of like a library form. Of course, there's, what's the library called in FFmpeg? AV Foundation, libav, or... Yeah, anyway. But of course that's all in C, which is great because it's like unbelievable. It's one of the most amazing open source projects, I'd say, FFmpeg. But yeah, we're doing it in Go just to learn and fuck around. Right. Let's what I wouldn't mind doing actually is for fun, we could just do very quick capture the packets. And then let's write that to, and then look, let's just have a look and see what WireGuard has. Let's just go. Write it out to yeah, sure. That's one question. You have one question left. Okay, what we're going to do is run this thing and then just let it capture the packets, and then let's do that. Alright. I just want to do something like, ooh, new feature. That depends. Depends on the application. Depends what you're doing. I see. Okay. So that's actually really, yeah, sorry. Okay. I misunderstood your question. Okay. Yeah, that's a good point. So in arrays, in Go, arrays are values. So when you return the whole array, you're actually like, you're copying it back to the caller. But with a slice, you're just passing back a pointer. So depends what you want to do, I guess, but that might help guide the decision. Usually you deal with slices. Arrays are really the exception. It's only when you're doing weird stuff, like for example, what we're doing here, where we very strictly need a certain number of bytes, and if we have any more than that, then it's like game over sort of thing. Also, because the values are so small, we can kind of just pass them around, not pass them around, but yeah, we can like copy them between functions and stuff, because it'll just do it on the stack, and then yeah. There is a good in here. Here we go. Actually, even just look at this. TV Josh, have a read of this document. So this is kind of old now, but it's a good one, and it's from like one of the original authors of the Go programming language. And there's a section there on arrays and slices, and it kind of just gives you like a way of general sort of best practice stuff. Yeah, but yeah, but no, it's actually a good yeah, it's actually a good question. Now, whether or not you should return pointers or values, there's a fun talk about that. This is also related, because a slice is really just like a data structure with, a slice in the array and blah, blah, blah. So I'll just do pointers, go for con AU 23. Here we go. This is a fun talk. If anybody's thinking about that kind of question, where they're thinking, oh, should I return a pointer, or
great, thank you,
or just return the whole value.
Good afternoon, everyone.
Then
it's a real pleasure to be standing here after what has been a day full of amazing presentations. Like, my head is spinning. Thank you for allowing me to.
I recommend that one. And there's like quizzes in it and all sorts of stupid stuff, so it's good. No worries. That's it. Yeah, I'm gonna rewatch this one. Actually, it's yeah, because I every time like I'm still going, what should I do? So yeah, I'm yeah. By the way, like this is why I'm linking other people, because yeah, I'm not an expert by any means. So we've got some packets in our in a file. So let's open that up in Wireshark. Just to, you know, again, get a little bit of a feel for it. Here, go to there. Okay. Cool. Okay, this is so relevant to what we were doing yesterday, so I'm glad this has worked out. So let me just turn the light on because I think it's super dark. Yeah, okay, give me a sec. Just adjust these things. Oops. Okay, hi. So this explains really nicely how what we were doing yesterday relates now to today. So what we've done here is that we've transported MPEG transport stream in the real-time transport protocol packets. So basically, I think that's it there. So yeah, cool. So the whole, that's the UDP part. And then sequence number, yeah, timestamp, sync source, and then bang, we go into the MPEG transport stream. If you remember, every single transport stream packet starts with the letter G. So UTF-8 or ASCII's 0x47. So this is all that we need to decode. Now, not really, but like, you know, for our first little test, let's give it a go. All right, let's get our header. Okay. Let's see how this matches up with what Wireshark thinks. Version, yep. Padding, extension, contributing source. Contains a CSRC identifier. I'm not sure what that means, but anyway. Marker bit. The 7-bit payload type. Okay, cool. Sequence number. Yeah, so that's the thing that increments every single data packet so that a receiver knows, like, you know, where it's up to. Of course, a timestamp. Hugely important in synchronizing stuff. Interesting though, right? Like, we've got the MPEG transport stream in RTP. So this isn't really like a super, you know, this is a little bit redundant, but it is like, this is what is done. So for example, if you buy cameras like, just to give you an idea where these things are used, Canon XF605. You get these sorts of cameras, which are kind of like these big things. You'll see like small news groups and stuff like that doing this sort of thing. One of the protocols that these things support is RTP. And one of the things it can do is MPEG transport stream in RTP. So there you go. Now there's other stuff that, you know, in a, yeah, like you wouldn't normally do that, but because there's a whole bunch of newer stuff, but this, you know, we're doing this just because it's easier, because we've just done the other thing. cool. Timestamp. SSRC identifies the synchronization. This is random. Okay. Sequence number. Timestamp. SSRC synchronization source. Okay. Okay. All right. Cool. Hey, Hands Effects being coded. Yeah. No worries. Let's get this thing. Oh, what the YouTube. Okay, and then let's do that. RTP. Oh no, we don't need that. We've got this thing. I guess we should actually export that, so let's see that unit 8. If the padding bit is set, the packet contains one or more additional padding octets or bytes at the end, which are not part of the payload. The last octet of the padding contains a count of how many padding octets should be ignored. Padding may be needed by some encryption. So how do we know? Okay, let's just do. The fixed header must be followed by exactly one header extension with a format defined in section 5.3.1. Yeah, okay, so this is kind of like this is really just a flag that tells us whether an optional part of the header is there. So we might not need to store that. We could just do our old pointer trick, but let's have a look. Contains a number of CSRC identifiers that follow the fixed header. And those are the CSRC was the content. I can't remember what that is. The CS contributing sources. Four bits, so let's store that in unit 8. Marker is important. The type is unit 8. And then here, I'm actually going to do, I'm actually going to set this as another type because I already know what I need to do here. I'll put it down here. So this is a uint8, and then we're going to have a few of these from that Wikipedia article. I mean, not from the Wikipedia article, but like there's a you know, there's a certain number of like, you know, important constant values that we need to be aware of. Okay, sequence is uint16. Timestamp is the clock frequency is dependent on the format of data carried. So this means that we don't actually know what this thing is. So really, we just need to store it as that. Because it's sort of, whatever's in the payload will understand what to do with this number. And depending on what you've got in your payload, like if you've got, yeah, like MPEG transport stream versus like, you know, some other totally different thing like Opus audio, then I guess how it interprets this clock, or the timestamp in here will vary. So, yeah, and there's quite a lot of information about the clock there, the timestamp, sorry. Okay, the SSRC field identifies the synchronization source. Okay, yeah, so that's a kind of a, so let's call this sync source. And yeah, again, this is going to be uint32 because we saw in the packet capture that it's kind of a, just a unique value. Identifies the contributing sources for the payload contained in this packet. Yeah, okay. So we don't really need that for us, but what we'll need here is, call it the contributing sources. Contrib. So we've got sync source and contrib source. And that is a slice of uint32. Because I think these identifiers are just kind of like, yeah, it's their arbitrary values that should be chosen randomly. And the max number of them can be 15. Okay. And then I think that's it. Done that. Let's have a look at this. So let's check. So we've got our timestamp, and then we're going to have our sync source. And then I guess we don't have any contributing sources. And yep. And that, yeah, we can confirm that because it tells us that there's 0, so there aren't going to be any. And then what? Boom, and then we're straight into the actual then we're straight into the payload, which is that you know, again, that G. That's the sync byte of our MPEG transport stream. Okay. So this is probably like the simplest. Don't need that. But the simplest thing. So let's do version 2. And that's just 10. So that's just a 2-bit integer. Yeah, okay. Could almost call it RFC 1889 or something. The value 1 is used by the first draft version of RTP, and the value 0 is used by the protocol initially implemented in the VAT. Oh yeah, that was like voice audio transport or something. Audio, yeah, I can't remember. But they talk about that, the history. So that's the thing before RTP. So let's call this version 2 a version... Or we could do 3550. And the value there is just UN8 equals 2. Call this draft, and then yeah, I mean, and that, yeah, I mean, we don't need a, yeah, the only one we're ever going to support is this, so. So we're going to have this thing, but then the actual packet is going to look a bit different, right? The packet is going to have the header. Then it's also going to have a payload, just like that. I think that's it. I mean, what's in the header here is going to be different. So, like that, we need to add more because there's all these things like a header extension. So this could almost be, I feel like it's going to be something like this. And then we're going to store a bunch of stuff in there. So this could be something like, yeah, I don't know. I'll have to have a look. Multiplexing RTP. Here we go, the extension. Let's have a look at this. Oh. Additional information required for a particular payload should not use this extension, but should be carried in the payload section. So really, look, I mean, we could have it, but just not do anything with it. Just store some bytes. This RTP specification does not define any header extensions itself. Yeah. So what's it saying here is that we've got a one. Extension header, only a single extension can be applied. Probably put this here. Sixteen bits is to be defined by the something like that, really. It's not it's not a lot, but the only thing I'm missing is this. The first 16 bits of the header extension are left open for distinguishing identifiers or parameters. The format of those 16 bits is to be defined by the profile specification under which implementation. Okay, so this is just could be anything. So this is almost going to be like the profile info or something like that. Profile, I mean, we don't know, but and it's going to be a uint 16, or we could set it as maybe we should set it as an array of 2 bytes, because who knows what could be in there. And then that kind of, yeah, I feel like that's clearer. Because those 16 bits could be used in any way. The length we know is like a continuous entity, and then everything else is just who knows. So let's do that. So we don't need the extension there because we're going to just do it by whether the point is nil or not. Padding. Yeah, I feel like I want the padding. I'm going to have to look at the padding. So let's just do a to-do so that we don't forget. Looks good. Let's put this up here and that also here. Okay, let's do some you know, we're going to do those. These are all these. So all those values 34. Oh, dynamic, interesting. Okay, well, anyway. MP2T, there we go. Let's do that. Probably, I think those names are actually, these are reserved in the IANA, which is like that Internet Name Authority, Name Number Authority, something like that. But yeah, we could almost do that, and then payload type 33. We're going to have a bunch of these. So one we could look at would be, why is the text so? just have a look at this just for interest. Payload format. Header usage. PT. Is a dynamically allocated payload type field one? And then that's all JPEG XS specific stuff. So what are we doing dynamically allocated? Type 112 RTP map. Ah, okay, I understand. Yeah, okay. So I see what they mean. It is like dynamically allocated in the sense that before, yeah, okay. So with RTP, what normally happens is that you've got some other protocol is used beforehand to like negotiate parameters and stuff. So this is a session description protocol. SIP is another one, session initiation protocol, and I think they're all used in like combination, and at the end of it you will get an RTP stream, but yeah, so that's why the payload type, that's how they can say the payload type is dynamic. And it looks like what they're doing is that the payload type they were saying is like you can have there's a bunch of values that are just, you know, reserved for dynamic allocation. So I think that was actually in here somewhere. Yeah. Okay, so that's saying it's dynamic, yeah, but when they're saying it was reserved. Ah, yeah, okay. Yeah. Okay, cool. That's all right. GSM, there we go. 2G. H.261 codec. Old. All right, that's cool. What are some of the biggest improvements to the gaming industries that I would recommend to have the greatest impact? So here's a fun fact for non-Australians anyway. In Australia, in New South Wales, the state that I'm in, which is the state that has Sydney in it, when they talk about the gaming industry, what they really are talking about is the gambling industry, because the gambling industry here is fucking huge. Like, for example, in New South Wales alone, at least last time I was, this was back in 10, 15 years ago at least, in New South Wales, it would have this, if New South Wales were its own country, it would be a country with the second highest number of gambling machines per capita, only behind Macau. which if people know is like this kind of like Singapore, like this little city island that is just full of casinos. So so some of the biggest improvements to the gaming industry that I would recommend to have the greatest impact would be to get rid of all those gambling machines. I keep some, but not so many. It's really bad. Like it's too much. Anyway, that's my gambling industry rant for the evening. Hey, morning from the colonials. Used to have social games too. Now it's all just pokies. Yeah, that's Actually, yeah, that's exactly. Yeah. There's a whole bunch of things. I think it isn't always like this though. They're like, no, you have to get rid of all of them, or you just leave everything as it is. It's like, God, like, can't we just work it out? Yeah. It's always like that. Like, oh, you can't just get rid of the pokies. I'm not saying get rid of the pokies. Just maybe, cut back a bit and put some social ones in there. That's just a great point, Panic Rascal. Yeah. Is this going to be like a single file package? Oh my God, every time I do this. Marshall. Okay, so data, and then P is pointed to a packet. Okay, cool. All right. So how many bytes do we need first? 1, 2, 3, 4, 5. So version plus eight. Oh, that's 4 bits. So 0, 5, 6, 7. Oh no! The version isn't so. The version is just 2 bits. Okay, let's just count this. Three, 4, 8. Okay, so we need 1 there. Marker bit is marker plus payload is 2. 1, 2, 1 plus sequence is 2 plus. Let's do it like this. Version padding extension count. Two, 1, 2, 3, 4, and then 4. marker is 1, and then type is 7. So that's another byte down. There's no sharpie. Yeah, what I noticed, I needed it for my shoulder and my neck. It was so like broken yesterday, and it was really not helping. Hey, by the way. Yeah. Like it was, I've got the Go fonts installed on in OpenBSD. Actually, it just comes as like it's in ports, the like Go font. I looked in pain. Yeah, no shit. I know. I looked over the last video to check like the audio and the sync, and yeah, and I noticed I was just seeing myself just going like this, and I thought, oh no way, that's yeah, not healthy. So I'm back on this for the moment. The only thing is that I do have a spare I do have a spare box I can use. Then I can just have a normal OpenBSD desktop again. I have one, but anyway, yeah, it can't drive a 2560 by 1440 monitor, which is the one I've got. So yeah. Oh yeah. All right. But the great thing about OpenBSDs is that you just say, well, I'm just never going to do any graphics stuff, which, you know, can be a good and a bad thing depending on what you do. If you're doing stuff like this, yeah, no problem. But maybe I do this only because I have to, not because I want to, hey? All right. Done that. Payload is, okay, so sequence is 16. That's 2 bytes. And we got timestamp. 32. So that's a lot of bytes. And then lots of information about that. So the sync source, 32. Okay, so that's at least how many we need, is this many bytes. So it's 1, 2, wait, 1, 1, 2, 4, 4. Need. And we have data. Okay, easy. Now we can very safely just decode everything. So, that's our structure. Put this, whoops. Go. And then we're going to go through, let's just check. Okay, and then we only want we only want this 1 2 1 2 3 4. That's the value that we want, just those 2 bits. This is a 2-bit integer. Next is padding. One, two, three. Light mode, day 2. Light, it's, you know, dark mode's over. Dark mode's not, you know, dark mode's, you know, it's gone mainstream. Remember when operating systems didn't have like a thing called dark mode? So dark mode got too mainstream for me. There's a There's a dark mode. I think what was the default background in Xterm? Is that because Xterm? I'm pretty sure the default Xterm like background is white, isn't it? Yeah. Well, there you go. Okay, the type. So this is a uint 8, and it's in the last 4 bits here. Whoa, no, sorry, hold up. No, I've jumped too far ahead here. The contrib count, sorry. Whoa, yeah, I've gone way over. Okay, hold on. Let's try again. Padding. Yep. Okay, extension we're not going to look at for now. And the CSRC count contains the number of things. Okay, and that we're also not going to care about. So let's just write a quick comment there. So the contrib count we also ignore. We'll ignore till later. That's what we want to do. All right, so that's 1 byte done. We good? Are we good to tell our manager about that? Hi manager, I've dealt with a single byte today. Pay me. All right, now we can go on the marker. Okay, marker, payload type. So this is OX7F. Now we don't want that. We want to then shift it right one position, because yeah, we want to shift it right because our binary representation looks like this. We've got the marker, and then we've got the payload type 1, 2, 3, 4, 5, 6, 7, like that. 1, 2, 3, 4, 5, 6, 7. Oh no, so actually, no. We're good then. Maybe we don't need to. No, sorry. Yeah, no. We don't need a shift because we've stored it okay. Do I? Right? 7-bit. Yeah. Oh no, wait. What's the beginning? Yeah. Cool. Okay, we've done the payload type. Okay, next. Now this is nice and easy. No 33-bit, 9-bit bullshit. This is just straight up 16 bits. Beautiful. From data 2 to... Oh. Okay, if my electricity goes, that's because there's a big thunderstorm starting. Okay, that's easy. Okay, p.header.timestamp. We read a uint32 out of that, and that's from 4 to 4 plus 4, which is 8. To, oh, uint32, so then it's, okay. All right. That's those ones done. Oh, sorry, I've just been having the chat. How do I get Acme on? Yes, that is it. Yeah, either add it to Inti or use a 9 wrapper and launch 9 Acme to UPS. Yeah, Inti will need to launch the plumber too. Yes, that is right. Yeah. Yeah, right. Oh, so there were outages in Melbourne. Yeah, I guess you guys have got bad storms down there too. I mean, up here we've only got rain, but it's coming from, you know, I guess we're blaming Victoria for this awful weather. I think on Linux, it's packaged, I think in Alpine, and I think it's packaged in Alpine, although I'm not sure. Arch has it. There we go. Cool. Yeah, I don't know about others, to be honest. Actually, I'm not sure. Yeah. In the Alpine jail. Yeah. Oh, yeah, true. Yeah. Actually, yeah, I have it in my Alpine VM. Yeah, on OpenBSD. Yeah. Okay. So now we need to handle the flags that we ignored. So what we want to get first maybe is... The contrib count, sorry, no, the contrib count we can actually deal with now, because what it's going to tell us is the number of, the number of elements that are there. And in our case, that's super easy. We can just allocate a slice up front and then just happy days. So let's do that. If it's 0, then I'll just call it CC equals so that bitmaster's OB. And again, that's actually just aligns nicely, so we can just go like, let's just do it like 4, 1, 2, 3, 4. Just like that. That gives us our count straight up. So we can now say if CC greater than 0, then we can allocate, like we can make a slice there. And I think it's an array of a slice of uint32. Okay, easy. So uint32, the length is going to be the count. It's cool. Now at the very end we've done that bit, so now we can look at the extension bit. Fixator must be followed by exactly one header extension. Yeah, right, okay, no, this is cool. So now we can actually just check the value of the bit and then unmarshal the extension straight away, if it exists. So that's cool. Now, do we need to do a check of the length here? 8, 10, 11, 12. Yeah. Okay. Now we need to do a length check here because we don't know for sure if we've really got anything left. It's a bit of a pain, but yeah. Do we get any other lengths? Oh, no, we don't need any other lengths because everything else is the payload, so we'll just move on. Go. Interesting. Cool. Okay, well this is good. Okay, let's check the value of that bit and then see if we need to unmarshal any more. So if data here we are. Good morning. Now. Hey, buongiorno. Sorry, I don't know any Italian. Buongiorno. Yeah. It's so weird. Like I remember I can speak French, and after like a week with living an Italian girl, I started to be able to understand her when she had conversations with her friends and stuff like that. It was so weird. like some words are quite similar and others are just totally different. So it's, yeah. Harsh language has that no. I say a week, it wasn't. It was like a month, so yeah. Yeah. Oh, and I'm gonna have to. The whole way now, I'm gonna have to check for the payload. This is so annoying. But I think I can put it in here. Yeah, I think, but. I can do the length checking, take away. Yeah, okay. Let's just try in here. So if the length, because we need now at least, where's our extension? Here. So we need 2 bytes, 4 bytes. So we need at least 4 bytes. So perhaps what we could do here is reslice. Right? Yeah. Could we? Yeah. Okay. Okay. We can tidy this up in a bit, but essentially, like we know we need at least. We know we need at least 12 bytes in the header. So if we get to here, then we know we can. Just a bit confused about where we get the this contrib counter and when we deal with the extension header, because both of them can exist. And I'm just not sure when, just understanding. It looks like if the extension bit is set, then the next thing must be the extension, the header extension, which is this structure here. Now, I feel like we don't need that length either, but because we're going to store it in there anyway. Just put it there for now. I think this has got to be invalid or something. I don't know. Maybe we just return. I don't know whether we return with an error or not. Here's what or empty payload or something. Do that for now, and then because I'm not sure whether this is really an error or not. All right. Now we're safe to. Yep. Okay. Now we're safe to reslice. So now everything after this we can try to deal with. Now, if we've got. start with that. We know the length is at least 1 here, but we can do a check here and say, well, we need, again, 1, 2, 3, 4 bytes. So if length of data is less than 4, okay, decode header extension need. There's this many bytes after the header, but we need that many. Okay, so that gives us a bit of well, there's the context and then also just a bit of like information maybe to help her caller. So that'll be now percent. So we have that many after the header, but we need 4. Okay. Now we're good to fill this thing in. I think we could just use a extension here. Okay, so profile. Copy the bytes from the next 2 bytes, 0, 1, 2. Oh no, we don't need to do that. We can just do that. And then what do we need after that? We need the length. We can get that just ourselves. So I'm not sure, I don't really want to store that because in Go, the slice, Go stores the length for us, so we don't really need that. Okay, we're going to read the uint16 from the next 2 bytes to 4. Yep. We could do a length check here just to see if it all makes sense. So, well, we're going to need to because we're going to start assigning in byte slices. So, okay, again, we go. Whew, storing the data. We could make a new I don't know whether I should try and like copy the bytes in or something like that. Turn into a slice and copy it in. Data equals okay, now let's check first. Check if we've got that many bytes. Otherwise, we're like it's just an invalid, so we can't do anything with it. If length len of data is less than length, then we go. A bit shorter reports. Yeah, the header extension reports the length that many bytes, but we only have that many. Okay, so let's go reports length. We only have data. It's probably a compiler error because we're doing uint 16 in an int, but whatever. We'll do that afterwards. So now we're going from 4 to length, like that. And then done that. Oh, had a ext. I feel like I could, yeah, whatever. Okay, great. So I think that's our extension done. Now we just need to handle the reslicing because we still may have payload and or we still could have this contribution count. So from here we where are we going to get that from? How do we know? Let's reslice here. Like that. Otherwise, we don't. We just go from 4. There. Okay. That, and then we're good. Okay, there, that's that done. Now we can start reading the contrib count. Now this should be pretty easy because it's just, we've already got the length of the slice. So we should just be able to go, well, again, we're going to check the length of data to see if we've got enough and then go on with it. So let's check of, how many bytes do we need? We need the length of this thing times 4. Just check that the identifiers are actually 32-bit. Contrib sequence number 32 bits each. Yeah, great. Read the sync source. Yeah. Okay, awesome. is a CRC list? Contributions. What does this thing stand for again? CSRC. Contributing source. Using the SSIC of contributing sources. Okay, contribution sources. Okay, we've done a length check. It feels like I'm writing C here. I'm just checking like lengths and stuff all the time. Okay, next up. If we're good to go, then we can just start looping through the contrib count. Now this is contrib count. That isn't actually what it's not contrib count. It's the contribution source. Yeah. Now we can just start reading it in. So we can actually just put the bytes in. So we're going to do this the cleanest way. We've got a bunch of uint32s in a slice of bytes. Really just do this. And then go do this. Oh yeah. So we've read and thrown away everything that we've already read. So all that's left is just from 0 onwards. So that's cool. So we'll go data I to I plus 4. And then we can do put into, oh no, sorry. No, we can't. Here we go. U equal, oh yeah, no. Okay, I'm gonna do var n. Okay, for I. So I need to do the index to assign the value without needing to worry about equals, so from n and n plus 4, and then we've read that many bytes, so n plus equals 4, and keep going. And then we can, I think then we're good to just assign the payload, yeah. So now that's easy because we know how many bytes we've read, so we can just go payload is the from n onwards, I think. And we return nil. Now, perhaps I could do if n of data no, I don't know if that's really an actual like error or not, but I'm just doing that now because I don't understand the protocol yet. Which is always a good time to write a library for the protocol, right? When you don't actually understand it. That and it look like it might be okay to be 0, but that's why I put that there. Like, let's just see what happens. Okay. I doubt this is actually going to compile, but yeah, there we go. Oh yeah, I already do that, of course. As payload type. Oh yeah. Yeah, I knew that would come there. Okay, the length is that. Oh, so let's just do the. And then I kind of want to. I just want to cast it straight away because I don't really care. Like, yeah. Because if we get some value that doesn't fit, then, well, I mean, well, one, it's impossible because we're passing it exactly that many bytes, but yeah, it's fine. Oh, header dot extension. Trip source. Now, what we could do is write a little command that listens on UDP, receives the RTP packets, and then I don't know, then does nothing. Just to see if it freaks out or something. I don't know. Alternatively, we could just write a little Marshall function that then, you know, that does the opposite of this. It shouldn't be too hard. Yeah, let's do that. We can just do so. Haiku4132. Hey, how was your day today? Yeah, good, thanks. How was yours, Haiku? Or how is yours going to be? Or how has it been so far? Oh, Jason. Cool. I can see that most of the complexity of the protocol actually doesn't really come in RTP itself, but more in the, because really this thing is just like transporting values around. I mean, really just values. And then, of course, like, for example, reading that JPEG-XS, there's a whole bunch of stuff in there to you know, be able to yeah, like what you need to actually get out of it. That's in RTP. So yeah, that's, you know, we've got that. Let's write a little command to now I'm gonna create a little UDP listener and see. Oh no, here it is. This, I even read that. Listen packet, isn't it? Oh, yeah, there it is. Just do, you know, 6969. Does that actually return an error? Oh yeah, it does. Okay. So let's just do pcon. Read from, yeah, that's the one, isn't it? Bytes read. Okay, the deadline here has got to be something pretty short because, yeah, I mean, like, let's just do that just because there's going to be some weird shit otherwise. Set deadline. And then, oh, is that a time or a, oh yeah. Yeah, okay, yeah, no. Let's just leave that. Okay. The is we could set the maximum size to be the MTU of the network, so it's going to be like with IPv6 is 1492. Is that right? Or I could just, yeah, look at Wireshark again. 1360 these ones are, okay. Be 14. There's a buffer size that makes sense. I just whoops. Can't remember. I think let me check this. I did this before with DNS. So when I wrote this little DNS package, I knew that I needed to, there was like a sort of a good buffer size that made sense. Oh, 1280, was that it? Oh no, that's a TCP. Oh yeah, okay. Well, that's probably the maximum size then, yeah. What's that, 1280 then? Let me do 1360 then. Oh, I just realized that the thing is like, it gives me a slice of bytes every time anyway, doesn't it? That receive read from. So it's irrelevant anyway. So I was thinking about something else. The packet con. Oh, unless it. Yeah. And then read from. Oh, no, it does. Yeah. Okay, great. So read. Okay. So con.read from into buff. And that. Let's just do this just straight up. Now we can unmarshal straight away. So we just go packet, whoops, packet unmarshal. Oh, it's RTP.unmarshal from buffer, and then let's do to the number that we read, and then to we need to make a packet. It doesn't give us a packet, so var packet. Maybe from now we can just print out the packet. At the end of it, we want to zero out the can't remember, does read from always read from the zero? Oh yeah, just copies it. Yeah, so that's actually it's fine. We can let it rewrite stuff, and then we don't. Yeah, we're only ever reading as many as we. Yeah, we're only trying to unmarshal from as many bytes that we read from the packet, so that's all right. Yeah, I think that might be it. What? No such file or directory. Looks like there's a file to me here. Oh, this is part of, yeah, this is a weird thing with the, okay, that's fine. I think there's a bug with that. Go imports where like it can't pick up new directories or new packages sometimes. Oops. Sweet. Hey, let's see if this runs. So how are we actually going to do this? We're going to maybe let's play Big Buck Bunny into our little program. It's not going to do anything other than maybe like, I mean, it'll log all the packets, but that's, yeah, that's enough. Oh. RTP is undefined, yeah, but you should pick it up for me. Yeah, so let's see if this actually works. Okay, so we're gonna read in from ffmpeg, real time, and then codec is is going to be RTP MPEG-TS. Copy the codec, don't do anything to it, and then I think that's it. Then just send it to loopback 6969. Is it gonna work? Nah. Need 0 bytes, only have 1316. What the fuck? Well, it was a good try. Fuck it up. Hey, how you going? Alright, so obviously, so when we try to unmarshal from there, here, RTP, contrib source. If need is, got the wrong way around. If the length of data is less than need. Cool. All right, well, okay, that's good. Cool. That's actually working. Instead of printing out the whole packet, let's print out something maybe like the sequence. I think that sequence one is interesting. Maybe let's have a look at what Wireshark. Oh, the timestamp. Timestamp's good. Okay, whoops. Oh, that's sending it. Right, just like that. Oh, okay, no, my bad. Oh, header. Okay, try again. Nice. Okay, there we go. Look at that. It's running. Awesome. Oh, you've been programming C# for 27 hours straight. I feel nulled. Fuck. Nulled like nulled? Does that even, I don't know, I've never even, to be honest, like I've probably seen like C#, like even just looked at like a source code file, like maybe 3 times in my life or something. your C sharp is going to be C blunt. Wow. Okay. Well, that's pretty good. We we got our little thing done. So if I do that again, it should just keep reading, right? It'll just see the same thing again. Yeah. Big jump. Quite understand that. It's like a really big jump. And you nailed that. We got some jokers in the chat. We got some jokers around here. It's good. They're keeping me entertained. I think wow. Okay. Well, that's good. It's actually pretty good. I might look. I might actually just call it there, and at the very least, like I'll cut it on YouTube, and then maybe I'll just stream on Twitch afterwards, just as a kind of like casual sort of working out what to do next kind of thing. Cause yeah, I actually don't know. So yeah, no, that's cool. Okay, all right. Yeah, as I said, so let me just hop back. Let me just open up this of what we kind of did today. So I guess MPEG transport stream, but which is not showing up. So let's. So this is all we've got so far. We've just got our packet, and we just decoded that we can manage the header. Yeah, that seems fine. So. Maybe we should try and oh, anyway, yeah. So I'm not sure what to do next, but that's